So I want to first just thank Dr. Nathan Tykocki for joining us. He is he's going to give a second part of this, as I mentioned before, and that's going to be in September. But today he's going to talk about 3D printing for the lab. Just a little bit about Nathan. He got a PhD in 2012 in pharmacology and toxicology at Michigan State University, where he studied vascular smooth muscle biology, physiology, and pharmacology, specifically as it relates to calcium signaling pathways and regulation. He is also a former postdoc of Mark Nelson at University of Vermont, and he finished his postdoc in 2015, got a K award, and then stayed on there at University of Vermont until 2019, when he came back to Michigan State University, where he is now as a professor, currently working on urinary bladder physiology, especially bladder fullness sensation and what regulates that. He uses all kinds of technologies, myography and Western blotting and immunofluorescence and confocal microscopy and so on and so forth. Today, he'll be talking about instrument design and fabrication using this really cool technology called 3D printing. And just a heads up for the next installment of this talk, where he'll get even more in detail, it's going to be next month, September 12th, Monday, same time as this.
Awesome. So, I first wrote this as, part one, 3D printing for dummies, but that's not fair. This is a really, really smart audience. And those are really, really lousy book titles. But I got into this, I don't know, almost 10 years ago now, out of being industrious and being cheap, and found that this technology is ridiculously simple to get going and remarkably underutilized in the lab. And so what I'm going to take you through today is just kind of the story about a little bit about how I got going with this, what we can do with the different types of technology that are easily and readily available, and how we can apply that to the lab. And then in the next set, I'll take you through the entire process of how we do it, from the design all the way down through to the making. And that's really for, if you take home nothing from this, I think the thing to take home is the idea that the design part of it is the thing that I think people have the biggest hurdle with, but it's the easiest thing to find help. And so the rest is just getting a machine to spit it out for you. So this is the problems that really got me going with this in terms of 3D printing. It's the sciencey stuff. All the stuff that we use every single day is ridiculously expensive. So that you see there on the right is like a quote from, I don't know, 5 years ago for my 4-channel myograph system from DMT. I guess their name is there. It's not their fault. It's like 50 grand. I could have bought a Volvo or an Audi for the amount I got this system for. And that's not to say that it's not worth it, but it's really, really expensive to be able to spend this sort of thing. And the other problem that we have is when we do this, we rarely get a device that we buy commercially that does everything that we want and everything that we need. And this is just a product of how retail works. You need to be able to make a device that meets as much as many things as you can for the most amount of people. And so what you see here is just a picture of a pressure myograph from my lab, and all the different bits of hardware that have to go with it. There's Warner Instruments line heaters and Ismatec recirculating pumps and Nikon microscopes and all of these different things that we hodgepodge together to make these systems, because each of them are built to be universally useful for a lot of different things, but be mostly useless for any one particular thing. It takes a lot to make it all go together. And then, the biggest hurdle I think that got me going is, we had in Vermont, and they still are, a phenomenal and talented instrumentation and modeling facility, IMF, at the University of Vermont, that has a long history of making, tissue baths and things for vascular research. And when you want something made custom, you pay for it. And so this was just one bath that was actually for a bladder that was able to just measure force. It was about $3,500. when it's actually maybe $100 in parts. Save that isometric force transducer, but that's another story for another day. So no matter what we did, whether I bought it from a company pre-made or I had a company make it, it's still really pricey. And, you know, this all really comes down to, for this sort of stuff, it's the law of supply and demand. You know, when you have things that you only sell a few of a year, like a confocal microscope or a multiphoton microscope, you have to make a lot of money and a little bit of stuff. These things are extremely complex to make with robust materials needed, because these are scientific instruments that need high accuracy and precision, and are almost all of them assembled by hand. Everything that we get that's inexpensive are things that companies can sell a lot of. That fabrication is simple, the materials are relatively accessible, the accuracy and precision may not be as important, or they selling enough of them that it offsets, or they can also automate production. And I think of this a lot when it comes to the advancements that we've had in microscopy work, in the cameras that we have of these ultra high resolution, very, very low light cameras. And we think that it's science that's driven it, these advancements, and it's not. It's cell phones. The needing better, lower light photo arrays for cell phone cameras is what's driven the advances that we've had, not the stuff that we've done. Because again, you can sell a lot of them. And this is exactly what happens with science, right? All the cheap stuff is still cheap for those reasons, but everything in science, this is what we run into. We're niche, right? You know, even Western blot systems, they're not selling 1 million of them a year. You're selling 1,000, maybe 10,000. All of these things are complex to make. They need these robust things. We need this high accuracy and precision, and it's almost always done by people. And so this all drives the expense of science through the roof. But the problem here is these are companies that are trying to make a profit. And so that's why things are pricey. But if you're not trying to run a profit, and with a little ingenuity, making these things is actually exceptionally inexpensive. And when I say things, I mean everything. And I see some of my students around here, they can attest to the fact that even down to like the test tube racks that we have for 50 mil conical tubes are 3D printed in the lab, because it costs $1 instead of however much you can buy them from, and we can make them whatever shape we want. So this is all relatively inexpensive when you're not trying to pay a lot of different people in the course of doing it. So in terms of 3D printing, this has become new to many of us. It's not new technology per se. It's been around since the 80s. The one that you see here is actually the 90s. You can tell by that wonderful man's very pleated pants. It's a 90s fashion fad for sure. These were all big $100,000 plus machines that were used a lot in the automotive industry for prototyping of different automotive parts. That's why there's a pretty big print area in there. But a fun thing happened in the 2000s, and it's called the RepRap movement. But that's reproducibility and rapid prototyping is in the about umpteen different acronyms that they have assigned to RepRap. But in short, the RepRap movement was an open source movement where they used printers to print other printers. So the idea was you could, in perpetuity, make things that make other things of themselves. And so many of the designs of these 3D printers that we see commercially that you can buy on Amazon now for a couple $100 are all based on this same simple RepRap design. And what this did is it really drove production costs through the floor. Because you could build these and print these little pieces that were needed from other printers, and you could do it in big old farms of things, and make these printers relatively inexpensively and simply. Also, I learned this in the course of putting this together. Fun fact that the first 3D printed organ scaffold was a bladder. So, you know, I'm where I'm supposed to be. I'm printing things, just not printing bladders yet. But we print everything else. So in terms of the sort of things that we have, it's relatively simple. 3D printers do one of two things. They either put plastic down or they build plastic up. That's it. So you either melt a filament like you see here on the left, and do it in layers, just like, building kind of like a cake straight up from the bottom. Or they do it in reverse, where you have this resin that they light with UV light, and they cure a layer, and they just build it from the bottom up. And we'll talk about both of these and how they work and the pros and cons for both of them as we go down. So the words that we're going to use, this get a few acronyms out of the way, because every good scientific talk has acronyms. The ones that we put plastic down, they call it FDM, or filament deposition modeling. Filament printing is what probably I'll say for the rest of today. This is, if you're familiar with 3D printing at all, is probably the one you're most familiar with. This is the idea that this solid plastic filament, it's about 1.75 millimeters in diameter, is shoved through a much, much smaller hole that's really, really hot. And the system uses an open source software to guide that nozzle through the different layers of your print and your shape. And after moving around a whole lot of times, voila, you have a thing. It uses a really, really wide array of plastics. And I think this is where the versatility for the lab is really there. And a lot of the plastics, and we'll talk some more about it, are things that everything else in your lab is already made out of. So we're not running into usually any problems where there's reactivity between biological tissues and the plastic that we're using. You're using things that are already common to the lab. So this sort of printer is the kind that you'd have in your house. I will admit, I am a nerd. I have one in the room next door. I bought it during COVID because I thought it was fun. And you can print, fidget spinners and all sorts of things for your kids, but also a lot of worthwhile things like we'll talk about today. So it is really versatile, but as far as in terms of all the different things it can print and the different materials it can use, but all things aside, the resolution is relatively low. So at best, you're looking at a 50 micron thickness per layer, where normally is most of the time it runs at about 200 microns. And really all you're sacrificing is time. So it is at least 4 times longer to print something at 50 microns than it is at 200. And if you're willing to wait, cool, but a lot of times you don't need it. So that's the FDM. That's the kind of the workhorse in our lab too. The other one that builds plastic up is called SLA, or stereolithography. And this one is actually really cool to watch, because like your thing kind of like rises from this ooze of this goo that it lives in. But it's the other way around. You have this build platform that squishes into this resin, and there's either a UV light LED array or a UV laser that cures a really, really thin layer of that photoactivated UV resin, and does the same thing layer by layer by layer as it rises. There are shapes and designs that you can do with this that are absolutely impossible to do with the filament depth, with the FDM filament printers, because gravity's not an issue, and we'll talk some more about that in a bit too. So there's all sorts of really complex and really high resolution things that you can do with this sort of stuff, but it comes at a cost, roughly 10 times the cost. But fear not, we'll get to the costs in the course of all of this. And I think for the most part, I tend to think of the cost of these things in terms of like how many primary antibodies it is. I think that's like a good an indicator for other scientists that do this. Like, how much, primary antibodies about what, $300 or $400. So I just think of things in like, how many primary antibodies am I using to buy all this stuff? So the printer that we have, and that, as I said, is the workhorse for us, is this one here. It's the Prusa, or Prussia if you're actually from the Czech Republic, the MK3S. And you'll see clones of this all over the place, but essentially this is the one that started it all in terms of the rep movement. So it prints up to 25 by 21 by 20. I don't know how better way to put that, but like, I don't know, 3/4 of a shoebox. So you can make some pretty big things on this printer. And they actually now have even a bigger one that you could, darn near print a motorcycle helmet on. Like I said, the resolution is 50 microns max. Mostly we roll at about 200. But these are all the things that you can print. I mean, it's basically everything. We'll talk about what those individual plastics are and what they do, but pretty much anything that can be printed in plastic, this printer can handle. And if you buy the kit, which is really fun to do, it's not hard to put together. They actually give you a bag of gummy bears with them and tell you specific times when you're supposed to eat those gummy bears during assembly. It's a good time. It's $800, so it's two primary antibodies will get you this printer. And plastics that you have there, those spools that you see up here, they run roughly 20 to 30 bucks a spool. That kilogram of plastic can print in, I wish I could give an exact number because it varies wildly, but it lasts a really good long time. It's a lot that you can get out of a kilogram of plastic when you're printing this stuff. And when we talk about resolution of this, I think this is a really good picture so you get the idea of print time relative to that thickness. So you see all the way at the end on the right, this cute little frog is their model. You can see there's these different layers in it. And as we shorten up that distance between layers, our print time just starts going through the roof. It makes it nice and smooth, but still you can see these different layers. And so this is the general idea. When we have things that we don't need unbelievable precision for, super smooth and all sorts of craziness, it's really ideal. Now, when it comes to the plastics that we use, the future, it's all plastics. There's really three big ones that you'll see out there when you get into this. The first one is PLA, or polylactic acid. This is one that if you do use in the lab, do not use it for anything that's going to see tissue or biological things of any sort. This is great for like tube racks and things like that, but for the most part, it's not great. And it's on purpose, like this is meant to be a biodegradable plastic. So it's meant to be broken down by bacteria, which doesn't really rock and roll real well with lab environment, and it also has the lowest heat resistance. The things that we use most often in the lab are good old-fashioned ABS. This is what Legos are made out of. So this is just, if you were to think of plastic that you would have, that would be it. It's tough, resilient, heat resilient as well. It's slightly flexible. I wrote here destroyed by acetone, but actually that's kind of a handy thing that I don't know, anybody that's tried to do acetone fixation of cultured cells in polystyrene knows that it melts the container. Same thing here, except we use this to our advantage. Because ABS can be melted by acetone, we can paint 3D printed things out of ABS with acetone, and it makes them waterproof because it seals up all the little pores that might be in there. And so it becomes really handy for making watertight chambers and things like that. For our lab, the thing we use most often is PETG. And if you have Nalgene bottles in your labs, this is what those Nalgene plastic bottles are made out of, is polyethyl something, I don't know, leave that for the engineers. It's kind of a balance between these two things. It's a little more flexible, easy to use, has a much higher chemical resistance, and is, all things aside, relatively inert. I have yet to find a time where this didn't work. It can be a little bit slower to print, but by far the most handiest thing that we use is this PETG stuff. So, like, what's the pros, cons? How long does it take for this sort of FDM printing? I mean, the pros, as I said, you can make nearly anything. And when we get on with this, you'll see some more of the pictures of the sorts of things that we make and how we make them. It's unbelievably inexpensive and versatile. When we get, again, to some of the examples, I'll let you know prices of how much it costs to actually run the machine. We've done the cost breakdowns to know how much it costs to run it and how much you spend per gram of filament. Pretty much absolutely anything now in your lab can become custom and disposable. So we even went so far as to start using these to make custom brackets for mounting to the heads of mice for doing intracranial imaging. We used to have these metal brackets that you glue to the heads to keep their heads stable, so you could do multiphoton imaging in mouse brains. And if it didn't fit quite right, just didn't fit quite right. And so now we were able to measure the mouse at the beginning, and before, you know, Tom Longden was done doing the surgery to prep the mouse, we could print out the right size, shape, and hole in that bracket, and glue it down as needed, and then just throw it away. We didn't have to worry about recovering it from the mouse after euthanasia. So this versatility is by far the biggest pro. I mean, the cons of this is printing can be finicky. We'll talk some more about that in a bit. And you know, you have to know your material in terms of, you know, if you're doing things that are hot. I mean, body temperature doesn't matter. These all things handle 37 degrees C, no problem. It gets different if you start putting boiling water and stuff and things like that, that you have to take that into account. And as I said, some are sensitive to common lab chemicals like the ABS and acetone. The PLA is actually sensitive to DMEM. So these sorts of things you have to think about. Printing wise, it can take anywhere from an hour to I think 48 hours was the longest we let something roll. You know, the machines are relatively user friendly. Once they're going and your thing's there, it usually finishes. I say usually. So, you know, it's kind of fun. You know, even some of the really complicated things, I just get the print going at, you know, 3:30, 4 o'clock, and I get back in the next morning, and voila, the thing that I needed is sitting there on the build platform waiting for me to use today. And so usually after those first 2 layers are done and you know everything's going to stick and stay in place, you can set it and forget it. As I said, though, there are some limitations in terms of size and other things. So in terms of shape, manifolds are tough. And what I mean by manifold is a thing that's sealed, right? So like a ball that's hollow on the inside is a very difficult thing to 3D print. And so we usually have to do them in pieces, and it's because it doesn't print. FDM is a little easier to do some of those manifolds, but you would never be able to access the inside again. So if you needed to seal it to be waterproof or things like that, this is not the ideal way to do it for doing jacketed, like water jacketed sort of things. The other thing is you have to be really cognizant when you're doing the design, and we'll go over that again the next time when I take you through that from top to bottom, that you can't have big old overhangs. And that's what this picture is that you can see over here is, oops, too far. These are overhangs, an overhang gauge that shows, like, as you can see, the farther that overhang is, you start to see this warping, and actually what you actually also start to see is drooping on the inside. So you can't have like a big bridge with a flat area that goes across the top. The filament will just sag. And so you have to, you know, get creative with sometimes printing things upside down or on its side or all sorts of different ways. All of these things are only rigid for FDM printing. There are flexible, I guess that's what I mean by flexibility, not versatility, and flexibility in terms of flexible plastics. There are some, but they are by far the hardest to use. So if you get really good at this, yeah. But I just, the heartache of it has not been worth the use and the things that we gain. So I tend to stay away from the flexible filaments. In terms of resilient, you know, the things that you're going to make are just as resilient as every other thing in your lab that's plastic. No more, no less. Maybe a little bit less than some of the, like, you know, injection molded things. But you know, the upside is, like I said, you can always just make another one if you break it. The last thing about limitations is some of these more exotic filaments that you can get, and there are some really bizarre ones. There's ones with, you know, metal embedded in them and all sorts of things. You don't know if those materials influence the outcome of your experiments, because there's not a ton of people that use these things in this way and do it in a way where they test that. So with you know, ABS and PETG, things that are already really common in the lab, you're good to go. But some of those more crazy things, you're going to have to do some experiments to make sure they work. So that's the FDM bit. This is the idea that, right, so you get a thing and it just prints it up layer by layer with a little nozzle, and you have a thing when you're done. The other side of this is, I say, you know, this is versatile printing without a budget. The one that you see here is also the one that's in our lab. It's the Form Labs Form 3. This company and this device came to fame because they do some of the orthodontics, like the Invisalign. It's not the Invisalign ones, but one of the competitors of Invisalign orthodontics. All of those are printed on biocompatible resin on a printer just like this, that they use because of its how accurate and precise that this is, and the very high resolution. It's not as big a print area, so it's like I don't know, instead of 3/4 of a shoebox, maybe 3/8 of a shoebox, but much higher resolution. Though that does depend on the resin. Some resin is really thick, and so they can't get as high a resolution. But like the flexible resins and so on, absolutely can get very high resolution. That's kind of the downfall of this system, is the resins are all proprietary. So I don't really know what's in all of them. Through experimentation, I've found ones that aren't reactive. Most of them seem not to be. But they also do have an entire line of biocompatible and implantable resins. So if you actually want to make devices that can go into an animal and stay there, in terms of implantable medical devices, this is your thing. They're already built for that. These resins are already tested and approved in all sorts of ways. So it's really neat what you can do from that aspect. And they have ones that are high heat resistance, I think, to the point of being autoclavable, because these don't use heat to cure them, they use light. And also some things that have really high tensile strength. So find me something that's really strong. This is what we use. But the price is obviously very different. So you're like at 9 primary antibodies, because you need not just the printer, but you need a wash unit and then a curing unit. Now, the good thing is that when you buy it as a kit with all of it together. But yeah, it takes up a little bit more space and it's more complicated. I don't recommend starting here. Start with the other one and move up to this once you've gotten used to it. There are other ones that are far cheaper, that are open source, that have more opportunities, but the support that came with this was useful when I was getting into it, and so I've really enjoyed staying with it. And so when I say that there's a workflow to this, yeah, there is. There's 3 things. So first, it prints just like you see on the left here, this device, but it's not fully cured. And there's extra resin in it. All of these resins are soluble in isopropyl alcohol when they're uncured. And so the next thing you do is you basically put it in a giant tank with a mixing plate at the bottom that stirs 8 to 10 liters of isopropyl alcohol around your thing for 20 or 30 minutes. And it dissolves all that uncured resin and rinses it away. And then after that, you put it under in this last UV case here to cure for anywhere from 10 to 60 minutes at temperature. And at that point, you have a solid as could be thing. And so, this is a multi-step process compared to the other printer. Like I said, when it's done, you just take your thing off and you go. So this takes a little more time, it takes up a little more space, but you're getting more robust and more precise things from it. So, just like the other system, yeah, you can still make basically anything. It's way more expensive, but more versatile, and you can do, these, the difference between these two really is the things that you make on the resin printer are solid blocks of plastic, where most of the FDM things are solid exteriors and shells, but they fill with just hash patterns of things to save on plastic. And so that's just, you use more material in the SLA. But by that very nature, they're all waterproof. They're all watertight with no extra things being done. And they're not limited by any of this bridging or manifolds or any of these things that I'm talking about. You can quite literally print absolutely anything within size constraints. I have yet to find something that couldn't be done on here with time. As I said, it's expensive. It's less clear about these proprietary resins. It takes more work, and that's a lot of isopropyl alcohol to be sitting in a container in our hood at all times, and it's constantly evaporating. So I got to constantly refill it. So we have a never-ending supply of isopropyl, 2-propanol coming through the lab. The printing times are the same. I mean, they're longer for some things, shorter for others. because the layer itself doesn't take all that long to print with the laser. The lower that you can put a whole lot of stuff over the build platform that doesn't go very tall, and it'll be a very quick print. Or you can put one thing on there that's really tall and it'll take forever, because the layers, the height is what takes time, not the other. So it's just an overview, a way deeper overview than you probably wanted, about all the different two real basic types of things, and that's the FDM and then the SLA. But now some more about like what printing is really like. This is what I always wanted it to be, you know, just like in Star Trek with the replicator, just be like tea, Earl Grey, hot, boom, there you go, or a martini. It doesn't really go like this. I am loath to show you the next one to admit the where things go wrong. But there have been more than a few times where I walked into the lab to a rat's nest of plastic like this, where layers didn't adhere right, or they broke free from the print bed and so on. To be fair, full disclosure, these pictures are not all my printers. They're from, we did a huge 3D printing project during COVID, making face shields for frontline medical workers. And these are all failed prints from part of our print farm. But there is a learning curve to this, to not have this thing happen. The good news is, these systems have gone through a lot of optimization, and to be relatively plug and play in terms of doing normal, simple things. When you get complex, and when I get complex, I mean speed, for instance, the reason these look like this is we were pushing really, really hard to print as fast as we possibly could at the lowest resolution to make as many of these as possible. And that's just, it was drag. The print head was moving too fast for this plastic coming out, and it just ripped stuff off. But if you just follow what comes with it, you're going to be in good shape. It does take, and with any fabrication and building everything, it does take some time. The right settings to your printer and filament are absolutely key. The bonus to this is, especially with the MK3S that we have and that I recommend to everyone, there is an immense database and forums and Reddits and subreddits and subreddits of people talking about this stuff, to get the absolute right settings. And I have met few groups of people online that are as friendly and courteous and helpful as the 3D printing community. There are lots of people that use, 10 or 20 of these machines in their houses, building all sorts of things all the time. And they are really helpful in getting these right settings and troubleshooting these problems in a way that I haven't seen from many other groups that I've been associated with. The design portion is what we'll tackle mostly in the next talk. But yeah, it's, there's some limitations to this of how you can design a piece. But the upside, again, with this 3D printing is we can be as simple as we need. You don't need to be overly complex. You just make it how you need it, and that's it. No fluff, no logos or shapes or craziness. You just make it exactly what you need and exactly how you need it, no more, no less. And really, I was just thinking of this today when, I was talking with my grad student Pragya about a Western blot that she did. And I was thinking that, troubleshooting 3D printing is no different than troubleshooting primary antibody concentrations and secondary antibody concentrations on a Western blot. You do a few iterations, things work, they don't, and you get everything sort of tweaked where you get this cool sort of flow that what works in your lab, and that's how it goes. The difference is you're not spending $400 a pop every time you do it. You're spending $1 or $2 of plastic. And so it's really, really a low bar for entry. So the next thing I want to talk about is just give you an idea about what we make and what can be made. And then some more about like the sort of software and the way to get in this easy. And these are just a few pictures of things that we put together. So we've done some superfusion chambers. This is about as simplest thing as you can print. The superfusion chamber was milled elsewhere, but beneath it, that green insert was just to perfectly fit the insert in a Nikon stage. Those stage inserts are ridiculously expensive. This plastic for this was, I think, $1.78 to make that. and it took maybe an hour and 45 minutes to print that, to give you a frame of reference, because I think you get that size in your head. So that way it just plopped right in there and held everything right where we needed it. We could put those screw holes wherever we wanted. We just, just put them in the drawing. These are just all sorts of different designs for different things that you can do. The one on the upper left, this is a chamber for a bladder for imaging that we do on the multiphoton. This is an insert to hold a brain slice actually in a six well plate. So it just plops right in the well. This was for intravital microscopy. So you could put Silgard in here and pin out a bit of mesentery. This was also an in vivo imaging rig that could hold the mouse on its back to isolate an abdominal window right here if there's another piece that went in there. These sorts of things. But then you can start bringing it together from these bits into more complex things. So this is a pressure myography chamber from our lab where these arms that hold the glass cannula, believe it or not, there's about a 50 micron blood vessel in the middle there. These arms are SLA printed that hold the cannula. Everything you see in gray is printed on the SLA printer as well because they're solid. You can tap threads in these. And so all of these pieces that you see that are plastic are all things that we printed in the lab. The only things that we didn't print are the manipulators themselves. And so this bath, to give you a frame of reference, this bath to buy commercially is $4,000 plus. There's about $32 in plastic here. There's a lot of hours in my design of it, but that was fun. But it's really, really, really inexpensive in terms of materials once you have the design there. And so, it's also just cases for things like this pressure servo controller. Holds it all together. And then we have entire imaging systems. Those who've seen any of my other talks know we do this whole pentaplanar reflected image microscopy stuff where we have a bladder on a stick and use these mirrors to take images of it from multiple angles. And everything in that system, again, save that manipulator, was printed on either the FDM, which you see here, all the things with lines in it are the FDM, so the filament printer, but the chamber here in this instance was printed on the SLA printer. Because it held the heat in a little bit better. Yeah, and so we can start to put this together with microcontrollers. If any of you are into like Arduinos and stuff, you can make all sorts of, my fat fingers there, nice Nathan. You can make all sorts of things that move, that you can control, measure force and tension and pressure and all of these things all together that all start with these pieces that we build on the printer. But the question I think to go from here is, like I said, I think the greatest hurdle in this 3D printing thing is, where do you begin with the designs? It is amazing how much stuff is out there, especially for science. That these are just three that I show here in terms of these models. There are just three of the repositories of stuff that you can download. You just have to search for things and you'd be surprised you can find. I needed, for a friend, they needed a very specific comb for their Western blot gels. And sure enough, I didn't have to make it. It was just there on Thingiverse. And he's like, Western blot comb. And it was the right size. And we just printed it and boom, there you go. And so even if you don't know how to design at all, there are these places where it's free, that the designs are given to you free, so long as you don't try to sell them. They're all covered under Creative Commons licensing, and they're there. And so you don't have to invent anything if you don't want to. You just download it and print it. The other thing that's interesting is this last company there, number 2.3 here, Shapeways. You don't even need a printer. They have very reasonable priced printing of multiple different sorts that you upload your design, and in addition to having their own designs you can download, you can upload your own, they'll print it and ship it to you. Granted, it is more expensive than printing it yourself, but still, you're talking in the $40 to $50 or $60 range for something instead of several hundred. When it comes to design, these days, there are tons of different ones. I think Tinkercad is one that is used an awful lot. All these other ones, yeah, I hadn't used half of these. Honestly, I used SketchUp just because I learned how to use that when I was a grad student. That's actually more designed for architecture than 3D printing, but I knew it by heart, so it works. And so everything that you see, I've done in an old guy sort of way, in this older software. The new, awesome thing is Fusion 360 is what most people use, but that's a really high learning curve. Many of these design programs for simple things are online, like websites. Then in the end, you just say, "Oop," what's they just download the file for you, this stereo STL file. And then ultimately, it's just playing around. Especially for Fusion 360, though, there is an immense amount of online tutorials and YouTube and so on and other places where you can just play with it. Ultimately, the nice thing with this too is all of these systems use the same basic file format of this G code, which these different programs, I didn't get into it here because we'll talk about it in the next one, but how it determines where that print head has to move is fairly universal. So as soon as you have this, you can put it in any software into any printer and get anything you want out of it. And if you think that, we're new to science with this stuff, we're not. The NIH in and to itself has an NIH 3D print exchange. There are lots of good things here. An awful lot of what you see in that still image from the YouTube video there's a lot of molecules and things to print. I find this really handy for class. Like I printed an IP3 receptor that was on there. So you could be like, okay, here's how the wings fit together. We printed, the catalytic domain from PKG, so you could see the way the dimer interacted and how these two things fit together. And instead of looking at it, in a picture or an animation, you have this giant thing that you could just be like, oh, here's how they fit, how it goes together. But all of these things here and the ones on the NIH and all that, it's all free. You could download these models and print them on your own. I think second to lastly, or maybe lastly here, there are, hey, a question in the chat. Oh, no, that's Chris saying put discussion questions in the chat. Sorry. So as far as the resources that are around, you may be surprised to find out there's a lot of these around your local university anyway. Check with your local library, both your city libraries or your university library. In a case here in East Lansing, both those libraries have these. Both my local library and the MSU library has what is essentially free printing for students. Or in terms of our local library, it's just for you bring your filament and you can use their printers. So there's lots of places to do this, to try it out before you make the relatively nominal investment in the printer. I have had wonderful luck talking with engineering students for the design aspect of it. Especially the mechanical engineering students are extremely well versed in most of these design programs, and they could be a huge asset. And they really like to do it because it gives them experience. So we've had a couple of undergrads do some work in the lab doing some design to help make that aspect easier. But as University of Vermont did, there are many times fabrication and design core facilities that go by multiple names. Ours is like the physics astronomy shop, but turns out they have all sorts of 3D printers that they know how to use and can help out with. There's always collaboration with someone like me at your university that knows how to do this. I do really recommend that you protect your IP with this stuff, because you never know how useful whatever it is you made is going to be to somebody. And it's far easier to patent these sorts of things than it is to patent pharmaceuticals or other chemical entities. When you have a physical thing that's right here, it's like, here, I made this, it didn't exist before. It's much easier and cheaper to sell your IP people on why this should be patented. But no matter what, even if you pay somebody to do the design of these things at $100 an hour, which is not an unfair rate, no matter what, you're still going to end up with exactly what you want and exactly what you need for the exact thing you're doing in your lab. No modifications, no additions, no subtractions, and you're still going to be cheaper than what you're going to buy from Thermo Fisher or any other company. And it's going to be what you want and what you need and the way you want it. But yeah, if you're still overwhelmed by all that, you can always come to part 2, so we can take you through the process, you know, soup to nuts, and show you how we do the whole thing. But that's really it. And so, you know, these are the different technologies that we have. It may seem daunting with a lot of different words, but really it's just the software does it for you. You just have to take what's in your head and get it in the computer. And once that happens, printing, it's pretty much the easy part. Everything in my lab starts just as it did 100 years ago, with a piece of graph paper and a pencil. And we just kind of sketch out what we're making, and then we do it. And I don't feel bad for the prototyping aspect of it, because like I said, you're talking about a couple of dollars. You know, that one system, that Prim system that I showed, I think that's, oh God, I'm well into the 20th iteration of it. But when you're printing it at a couple dollars a pop, you know, what's 40 bucks? You know, so what? That's nothing. As soon as I think that machine, I think in the end, that first time, the first printer that I bought, and for the amount of prototypes I had to make for that GoPro adapter for my microscope, it paid for itself versus what I would have paid to have that printed just in that first time. Because I think I made 6 different prototypes of that, and that would have been $1,200 through my instrumentation modeling facility. So yeah, and even if you don't have the designs, all these things are there to print, and it just changes the world to be like, okay, I need to do this thing. Okay, let's just make it. Let's just make the thing we need. And it's not nearly as daunting as it seems. It's just getting the idea in your head. So yeah, this is more fun when we do this in person, and I can like throw you things that we made, and so you can get it, like feel it and see it and be like, oh wow, this really is not janky. This is really a good thing that we could use. You just have to trust me from the pictures. But it really is surprising how it is. So yeah, thanks, and I'll answer some questions. So we got one question. Thank you. With the biocompatible fillets, any data about materials do with long-term exposure to urine-like liquids? I don't know. Probably not. That's usually outside the scope of what they do. Most of them, the biocompatible ones are looking at immune response related viability, because most of the plastics are resilient to the pH that you would have in urine and other things. The things that they're looking for with the biocompatibles is that they're not going to cause massive inflammation. You know, like how you coat things in silicone before you implant it. You know, they're looking for things like that. Biologically inert is mostly what they're looking for in the biocompatibles. But I don't know. That's a really good question. I will tell you that the Formlabs people are always looking to say how their stuff are used in new and different ways. And they're the kind of people that if you asked, like, hey, what happens if you stick this in pee for 3 weeks? They'd be like, we can try that. Or at least they'd send you a sample that you could do the same with. So it's pretty easygoing like that.
So Nathan, the thing that is like the black box, well, one of the black boxes to me in all of this is you say you can get a graph pad and you can sort of sketch out what you want, and then you just get it printed. But isn't there like a middle step there where you have to code it all?
Yeah, you don't have to code it. So you have to use some of that design software, and that's to use. And this is why when I give this next talk, I'm actually going to like put design software up there and show you the basics of, I mean, I actually could probably do that if we don't really have time now, or I could have, but you can see the basics. The CAD software has come so far from where it was in the 90s, where you had to like, you know, CNC machining, so computer numerical control, that was an associate's degree, right? To like code this stuff. And you had to know numbers and positions. All of it's graphical now. So you basically make a box and you click a button, it extrude, and it makes that box into a cube and in the program, and then you can manipulate that however you want. It's basically just moving cubes around, or circles, or triangles. And then you export it as this stereolithography file. And the software for the printer does the rest. And so that hurdle of that, it's much more graphical now. It's much more user-friendly and intuitive for how to do it. You don't have to write code at all. in any one bit. You're basically using a program that is not indifferent to Adobe Illustrator or Photoshop, but you're just using it in 3 dimensions. It does get weird with some things. Spheres are really confusing to do, and a lot of times you have to draw in extra stuff that it misses, because in the end it all makes it into triangles. But it's not worth getting into, like this is just minutia of it. But yeah, it's not like the old days that really you just need to get into any sort of design program that can be 3D. And honestly, even Illustrator can do this because it's vector based. You can make a 3D object in Illustrator. If you're really good with doing the 3D perspective stuff in Illustrator, you can get to a format that can be turned into a 3D printed object even there. I don't recommend that, but these other ones are really simple, like that Tinkercad, and do it, and it'll take you right through and be like, yep, here you go, you do a test thing, and the rest it just spits it out. It's really, they've taken the complexity out of it, and really it was this open source movement that did it, that brought this to everybody.
So, like, what are some lab materials that everybody uses? Some examples of things that a lot of people use that could be done with this.
So oh God. So for us, the simplest thing is all those blasted racks that they're like $40, right? And you're looking at it, you're going like, really? $40? Because they either have too many holes or the wrong size holes or not the right mix. And so we use a very specific set. So ours is 2 tubes for 50 mil conical tubes, 2 next to that for 15 mil conical tubes, then for 2 mil microcentrifuge tubes, and then the 0.5 mil microcentrifuge tubes, and like 10 across. And so it's just very compact, and we have the right mix and match, and we can rearrange it and we print it. And so we have this little platform, and it's like, again, a couple bucks, and then we have that platform right there. So everything in your lab that's plastic or has a shape, and even some things that aren't, could be used. But it's stuff like that where it really catches up with itself, because you don't realize, unless you're young assistant professor like I am that just started a lab, how quickly you really realize where the money makers are for these companies. And it's not the Western blot systems. It's all those little things that cost an exorbitant amount of money, like holders. The Warner inline heater has a holder that goes with it that is like $60, and it is 70 cents to print it. And it took 5 minutes to code just with a caliper and just measure it to draw it in the system. It's just like a box, and take the sides down and the middle down, and there you go.
Dr. Popovich has a question in the chat. She's starting up her own lab, so she might have some particular needs that she can think of, but she's asking about a scanner for design.
Yes, so Petra, they have them. I've not used them for our stuff because most of the things that I print are have a lot of concavity to them. The 3D, my experience of the 3D scanners is it's good for things that are convex a lot, like a bust of something, or a vase, or a thing that has an outward shape. They have trouble with the shadows of things that go inward. And so we've done a little bit of it, and it's been useful for bigger things. But that technology is forever improving, and I want to get more into it, because that would make life a lot easier if we were able to get a 3D scanner. And they do exist, that it's like a platform with a camera that just rotates an object and takes images of it as it goes and looks for contrast to understand what's what. And they're really getting to be quite good. I mean, some of them even are as simple as using an iPhone with an app, and they do it. So I haven't used it, but simply because the level of complexity and the size of things has just usually precluded using it. Because you have through holes for flow in and out of stuff, and that just doesn't get caught. But you sure as heck could. Frederica, yes, I have printed polypropylene. Of all the things that I never want to print again, it is polypropylene. No, it's doable. It's one of the harder things, because polypropylene as a plastic has an odd thing that it doesn't like to stick to itself. It's a very non-sticky plastic. And so it's very good to extrude if you're a company blow molding something, right? So you have a mass of polypropylene, you can blow it out into a shape. and it sticks together well, and it doesn't adhere to the mold like some other things do. I'm sorry, I'm a little bit of a nerd because my brother-in-law is a plastics engineer, so I have somebody to talk to this about. But it's hard to get it together. That being said, it can be done, and I did print some 24 well plate inserts that had screens in it for whoever it was doing C. elegans, and they wanted the eggs to fall through the culture, but the worm to stay above. And so we printed an insert that popped in, and it could be done in polypropylene. So the sterilization is tough. That's a really good question, and I'm glad you brought it up. It all depends on how and what you mean by sterilized. Autoclaving, in terms of the traditional high temp pressure autoclave, I don't think any of the things that are printed on the FDM printers can take it, because all of them are extruded at about 270 degrees Celsius or lower. And we start getting near that when you start adding pressure and all that. You start getting well into the point where these plastics will bend and flex and sag. I will say that the UV box for sure, that's how we do it. So because almost all of the filament printed ones are not responsive to isopropyl alcohol, unlike the other one, we just dunk it in 100% isopropyl alcohol for a while and then stick it in a UV box. Yep, it's exactly how we would do it. There are some high temp ones of the resin that can be autoclaved. So you could do that in the traditional high temp, high pressure autoclave. Their temperature difference, because those are cured by UV, not temperature. So some of them are extremely temperature resistant and can be done that way. So yeah, you could make that for sure.
Thank you so much, Nathan. This has really been educational, and I look forward to part 2. Thanks everybody for coming.
You bet, Chris. Thank you. Thank you everyone too. And good to see familiar faces. We'll see you next month.